let's start coding.
Welcome to the final video in the feed-forward neural network series, where we'll be coding our more complicated neural network using the gates that we had developed in the previous tutorials. In this neural network, we will have one input layer, one hidden layer, and one output layer. In the input layer, there are three inputs, x1, x2, and x3. In this tutorial, I've already pre-coded everything so that you all don't have to wait if I mess up on the code. We already know this code works. So I'm going to define a class. I'm going to call it net2 for our second neural network. I'm going to define it as three inputs, x1, x2, and x3. We're going to set those to 0 for now. I'm going to define a step size. I'm just setting that to 1 for now. And then I'm going to set an expected output. This is what we expect the neural network to have. So our outputs of 0, 1, 1, 0, if we are given these respective inputs, should be the values that we plug in for our expected output. We're going to have a hidden layer that converts from 3 inputs to 4 outputs, which when we look at our model that we developed is exactly what happens. We have x1, x2, x3 going into 4 neurons right here, and then those 4 neurons each have an output, which means 4 outputs. So 4 to 1 is what we're going to be defining here, right? So we have A1, B1, C1 for the first neuron, A1, B1, C1. A2, B2, C2 for the second neuron, and for the third neuron, etc., etc. And then the derivatives for those respective synapses so we can correct those weights later. The derivatives so we can correct those weights later. All right, and then now we have one more thing where one more layer where it takes 4 inputs and converts it to 1 output. And so as you can see, we're going to take these 4 things that we're getting out of our sigmoid functions here, and then we're going to convert it to our output right here. So this is basically acting as a hidden layer, and then this layer right here also contains synapses that convert the 4 to the 1 here. So you can see that is defined here as A12, B12, C12, D12, which should correspond to A_2. I'll add the 1 later maybe, but you get the point. A_2, B_2, C_2, D_2 is equal to these values right here in the code. And then the derivatives for those respective synapse weights for that particular layer. All right, and then now we define the output of the whole neural network as out, just self.out, because that's the output of the neural network here. And then the derivative of the output, which we use to train our neural network later on during backpropagation. So that's all there is for the setup of the neural network. And then we can activate this neural network, right, by using the gates that we had previously created. So there are multiply gates for A1, B1, C1, which is A1 multiply, B1 multiply, C1 multiply, which are these 3 right here. And then there's an addition block. There's a 3 addition block that takes in the outputs of these multiplication functions. Y1 is the output of those multiplication functions, and it adds it together. And then we activate it to set those wires here. And we do that for the second node as well, so the multiply function here for those 3 weights for the second node, and then we add them all together, and then we pass it through the sigmoid. So second one right here, multiply, add, sigmoid, and we set these 2 wire weights until now. Node 3, same thing, multiply 3 of them, right? A3, B3, C3, add them together here, right? Add them together here to this addition block, and then put the sigmoid function. And then now we have the value for this wire, and then we do it for the last node as well. And then for the hidden layer, what we do is we take these outputs that we get from these sigmoid functions. So I got that first sigmoid function output, and then I pass it in as an input to this multiplication for that synapse, which is exactly what's going on right here. I'm multiplying that synapse, I'm activating it, and then now this wire is active. Same thing for B, same thing for C, same thing for D, and then we keep doing that, and we add them all together at the end because there's an addition block, and you can see that this addition is add 4 because we have 4 inputs that are going in to this addition block right here. We add it, we activate it, now we get this wire value right here. We pass it through the sigmoid function, activate that too, and that's the output for the entire neural network. That's the output for the entire neural network. So we have done forward propagation. Let's go do backward propagation. And let's take a look at this right here through the second neural network. Let's backpropagate. We're going to take the error of the output, which we're going to calculate later. Right? We're going to backpropagate, which is going to give us this value right here. And then we're going to set that equal to the addition blocks error. Right? That's the addition blocks derivative right there. And then we're going to backpropagate again, and then that's going to give us the values for the multiply function error output. Right? There's 4 of these multiply function error outputs, which are 1, 2, 3, 4. We set the multiply error outputs to the add blocks outputs, right? And then we backpropagate. And backpropagation lets us get these values, these error values. We know there are intermediary synapses, right? There's DA underscore 2 in this instance, underscore 2, B, C, and D, right? Those four. We set the derivatives for those values, right? We set the derivatives, and then we backpropagate this multiply function to the inputs of the sigmoid function. This is the secondary derivative, right? There are two derivatives for the multiply function, one for the A input, one for the B input. And so we've already set the B inputs because the B inputs correspond to the synapse weights right here, A underscore 2, B underscore 2, C underscore 2, D underscore 2. And the other weights are the sigmoid function inputs right here. And so that's what we set the outputs of the multiply function backpropagate to are the inputs of the sigmoid blocks backpropagation. So we have the sigmoid 1, sigmoid 2, sigmoid 3, sigmoid 4, which correspond to 1, 2, 3, and 4 in the neural network. We backpropagate that. We set all of them equal to their addition blocks inputs for the backpropagation, the outputs of these sigmoid blocks, right? So now we're here, and then we set that equal to the additions, and then we backpropagate all those additions, right? And then once we backpropagate all those additions, we have 3 wires that are coming out of each of them, and each of those 3 wires are going to a multiply block for each node. So there's 3 wires, multiply block, 3 wires, multiply block, 3 wires, multiply block, 3 wires, multiply block. And that's exactly what's going on here, is that we'll go back and we'll look at these, and then you see 3 wires here to those first multiply block, 3 wires to the second, 3 wires to the third, 3 wires to the fourth. And then we backpropagate those multiply functions, and then in the end we can actually just throw away the derivatives, one of those derivatives for the multiply function, because those are the inputs and we don't want to change the inputs. And what we're going to do is we're just going to change the synapse weights, right? DA1, DB1, DC1, DA2, DB2, DC. You get the point, right? We just essentially go through and update all these derivative weights. And so now we've done with the backpropagation, then we're going to start training the neural net. First we have to activate it so all these wire values go in. Then we have to calculate the error, and so the error is the expected minus the actual output that we get from our activated function. Then we're going to backpropagate it with the function that I just talked about. And then we're going to update the weights of the synapse in layer 1, A1, B1, C1 using Newton's method. Look at the other videos if you don't understand what I'm talking about. And then we're going to do the same thing for the second hidden layer, A1 underscore 2, B1 underscore 2. And in this case, it's these weights, A underscore 2, B underscore 2, C underscore 2, and D underscore 2. We updated all those weights, and we've essentially trained our neural network once. And so that's how our neural network with one input layer, one hidden layer, and one output layer works. If you can understand how this works, you can see how you can create neural networks with more hidden layers, more hidden nodes, etc., etc. And for all these tutorials, we've been using the sigmoid function as our gates. But as you can see, you can replace these sigmoid functions with whatever functions you really want, like tan h, or maybe ax plus b, or whatever sorts of functions that you really want to here. And that's what the beauty of the neural net is that you can actually change what those gates are. And you'll see that that's what they do for convolutional neural nets. They'll have a function that'll do something else for each of these gates, right? Like maybe edge detection for each of these gates, etc., etc. That's for another tutorial. But if you can understand how to create this neural network and how to backpropagate it and do the feed forward as I have explained, then you will essentially understand the basis of neural networks. And this is what I'm trying to explain into this video. All right, so we're going to do the second problem in our PowerPoint in the PDF. And remember, our inputs and our outputs don't exactly correlate, only except for the fact that if x1 and x2 are different, then the output is 1. If x1 and x2 are the same, the output is 0. And so that's the difference between the neural network we trained in the previous two videos before this one compared to the one that we have here. But the process is the same. We'll create a neural net. We'll just go ahead and set our input values. We'll just go ahead and activate the neural net just for fun, right? That's just for fun to print out the synapse weights and the synapse values. So we're printing out the synapse weights and the synapse values here for the hidden layers and the output layers. And so those are all the synapse weights, and then you'll see them change at the end. We're going to display the data before training. We're going to do our first input, 0, 0, 1, 0. We're going to do our second input, print the output. We're going to do our third, and then print the output, and then you'll see the values will not match our expected. And then we're going to train it, maybe overtrain it. I know this is called overfitting the data, but this is just to try and understand how the algorithm works. We're going to activate our first one and train. We're going to activate our second one and train. Third one, train. Fourth one, and train. And then we're going to do that 100,000 times And then you'll see that when we have a prediction, that you'll see that it'll predict it to be the correct values. And so we're going to print out the synapses after the training, and then we're going to show you that the predictions match our inputs. This is essentially overfitting the data of what people have mentioned, but it'll explain the process of how neural networks work. All right, so I know that was a bit rushed. I didn't have too much time in this video. I think YouTube's limit maybe 10 minutes. I don't know. Anyway, so let's run the code and see what we get. All right, so I'm printing it out as a percentage done. So we're training the neural net. Before training, you can see these values do not correlate whatsoever. Right? They're around 0.5. Right? They just normalize to 0.5 regardless of what the input is. And that is to be expected if you understand what the sigmoid function does. But now we're going to see what our output is once this is done training. And so we're at 52%. Cool. So as you can see, these are the synapse weights for our layer 1 and the synapse weights for our layer 2. Just printing them out for your sanity, right? And then almost done. I want to make sure that y'all see all of this so you know it's not voodoo magic that's happening in the background. And I probably don't need to train it this much anyway, because we're definitely overfitting the data. All right, so we're done now, and we have our synapse values. And you're like, okay, that doesn't make any sense, and nor should it, because you really don't know what's going on here. I mean, you can see 7, -7, -9, and 9, but there's just these patterns that emerge that you just kind of have to look at it and try to understand with these hidden layers. It's like, oh yeah, I can see a pattern, but you can't actually predict those patterns emerging beforehand. Unless, I guess, you're a genius. Maybe you can. And so here we can see our inputs are 0, 0, 1. It should be 0, and it's pretty close to 0. It's 0, 1, 1, and our inputs are 1, and it's pretty close to 1. 1, 0, 1, our inputs are 1, pretty close to 1. 1, 1, 1 should be 0 because there's the same value, pretty close to 0. And then as you can see, we have trained our neural net. And if you understand how this works, then you'll understand the tutorials that IamTrask has had with those 11 lines, build a neural net in 11 lines. Look at that again after you have this understanding. Look at Siraj Raval's 4 minutes, neural network in 4 minutes, and you'll understand how these things work, the nuances of how these things work and how to train neural nets. I hope these series have been helpful. I'm thinking in the future I'm going to do something with genetic algorithms and potentially neurogenetic algorithms. I know a lot of people have expressed interest in that, right? Where given no essential model of the world, just go ahead and play a game and be really good at it, or just give it a goal and see if it can achieve that goal somehow. And so not so much data science, but artificial intelligence. So thank you for listening, and yeah.
Oh, yeah.